Hello. In the first video we looked at creating first order differential equations like these ones up here. In the second half we're going to look at a standard process for solving them. We're going to split the variables, we're going to integrate both sides, and we're going to add our initial conditions. We'll have a solution for each problem which we can use to predict the future values, and quite a lot of these are going to prove to be exponential growth or decay, but they don't have to be. So simple first one. The rocket's going up into space. F equals ma will give me this equation, dv by dt equals minus g. Well, we're just going to integrate both sides as it stands. So on the left hand side I've got the integral of dv, yeah, and on the right hand side I've got the integral dt. So what do I get? I get v on the left hand side, I get minus gt on the right hand side, and I get my constant of integration. So I need to deal with my constant of integration. How do I do that? Well, I'm going to sub in some initial conditions. So let's say that when the rocket starts off at time t equals 0, its initial velocity is v0. I can sub that into the equation above. So v0 equals minus g, t is 0, so that's going to go to 0, isn't it? That's going to e plus c. Therefore c equals v0. So I can put that back into my equation, my formula here. So I've now got v equals minus gt plus v0. So what's that telling us? Well, we're starting at v0 and our velocity is going down from being positive, and then it becomes negative. So our rocket would start off going up, and then it starts coming down. Okay. This is a very common setup that I'm looking at here, and you'll see this one turn up a lot. And I'm using the investment model here. So the growth rate of my investment, yeah, that's the rate of change of my investment, dv by dt, is proportional to the amount of the investment at that time. So I've put in my constant of proportionality, and it's going up. So k, I've got a positive k. What's the first thing I do then? I'm going to split the variables. I want all the v's on this side, all the t's on that side, and if I do that, then I can integrate it. So let's have a look and see. So how do I get that? Well, I multiply the whole equation by my dt, and that brings the dt from the left hand side to the right hand side. That's good. But I've got a v on this side, haven't I? I want to get rid of that from the left hand side, and it's a multiple, so what do? I divide the equation by v. So what have I got? I've left with 1 over v times delta v, and on the left hand side, on the right hand side I've got plus k dt. So that's all ready to integrate, isn't it? Because all I have to do is write my integral signs in front of it now, and I can integrate it. Well, I know how to integrate the left hand side. 1 over v dv, the integral of a ln, sorry, of 1 over v is going to become the ln, isn't it? So there's my ln v. On the right hand side, well, I'm just integrating a constant dt, so I get plus kt plus my constant of integration plus c. So what's my next step? I've got a formula. One thing I will do, I don't really like having this in a form ln v. I want to find out what v is. So what am I going to do? I'm going to power this up. So I'm going to make those the powers of e, because if that's the top's true in terms of powers, then this new equation must be true. Left hand side, e to the ln v is just going to be v. Right hand side is going to be e to the kt plus c. There we go. But of course, if I'm adding two powers together, I can split that out into multiplication, can't I? So I've got e to the kt times e to the c. Well, e to the c plus c is just a pretty complex way of saying a constant, isn't it? So I'm going to replace e to the plus c with an a. And if I do that, I can write this equation as being v equals a, some constant, some multiple of e to the kt. Okay. What's my next step? Well, I want to deal with my initial condition. So let's assume when t equals 0, the value equals v0. So if I put that into the equation, I get, I'm just going to move it up so we can see it, I get v0 equals a, lots of e to the kt, k0. Well, e to the k0 is the same as e to the 0, isn't it? Which is 1. So I've got a 1 here, haven't I? So that just tells me that a equals v0. And if I substitute that in, I've now got a nice complete equation that v equals v naught e to the kt. So what's that tell us? It tells us that my initial value is v naught and that I'm growing exponentially, and my constant is k. So I'm going to have a graph that looks like that. Let's have a look at another one here. Let's have a look at temperature of water in a kettle. So the water's in a kettle, we boil it, so it's probably around 100 degrees C, so that's our T naught. Yeah, and then we let it cool down over time. It's going to decay. We're going to see why it decays in a sec. We'd expect it to decay in physics, wouldn't we? Till it reaches the temperature in the room. So here was my equation. Okay, what do I need to do? Well, I need to get all my little t's on this side, so I'm going to multiply dt. I want to get this bracket here, the t minus ta. I want that on the other side to be with the dt, so I'm going to divide by that. Yeah, all of these, as you can see, they're direct proportion, aren't they? There's no constants on the ends. Yeah, one increases, the other increases. So here I've got my new equation. There we go, 1 over t minus ta multiplied by dt. On the right hand side I've got my minus k dt. What am I going to do? Well, I'm just going to integrate both sides, aren't I? So my equation will be the one written here. And what am I going to get as my integral for the left hand side? Well, I'm just going to get ln of t minus ta. On the right hand side I'm going to get my minus kt, and I've got my constant of integration again. So I'm going to do my common rearrange, in which I'm going to power this up by make those the powers of e. So on the left hand side I've got t minus ta, the right hand side I've got e to the minus kt plus c. I'm going to do that same trick of splitting off the e to the plus c, and I'm going to replace and write that as an a because it's just a constant. And now I've got t minus ta equals a, some multiple I don't know yet, of e to the minus kt. So what am I going to do? I'm going to put in my initial conditions. So let's do that. When t equals 0, let's assume that the temperature is t naught, yeah? So let's have that there. Good. And I substitute that in. Well, I've got t naught minus ta on the left hand side. Here I've got e to the minus k0. E to the minus 0 is 1. So I've just got a left here. So I now know that a equals t naught minus ta. I substitute that in here, and I've got my equation for the temperature over time. That will be a graph, won't it, if I graphed it? Well, I know that my initial temperature is t naught. You can see here that as t tends to infinity, this value here is going to go to 0. So the t naught minus ta goes to 0. So I'm going to end up at ta, aren't I? That makes sense. That's what we're expecting to happen, wasn't it? So I've got exponential decay until it reaches ta, and for any time I could put in a value of time and I could just find its value somewhere along there, couldn't I? So there we have it. That's my video on solving differential equations. We take our differential equation that we've worked out, we then split the variables. So I have one variable on one side and one variable on the other. I can then integrate both sides. I can put in my initial conditions to find my constants, and that gives me a equation, a formula for my either temperature here or value of my investment. I can work that out for future values, and typically these type of equations here are going to create exponential growth or exponential decay, which is what we see in the world a lot. So there you are. You can copy that down. Best of luck.